So today we are taking a look at adding and subtracting fractions that don't have the same denominator. Now, we hopefully remember from before when we did adding and subtracting fractions that in order to add or subtract them, they have to have the same denominator. So if I'm going to do this, I got to make them have the same denominator. Now, to kind of visualize why and how we do that process, I'm going to go to the old pictures that sometimes are used with fractions so we can see what's happening here. So each of these rectangles represents one whole. Well, out of this, I can take the first one and cut it up into thirds, and the second one cut it up into fourths, so that I can then represent each of these. So the first fraction, that's going to be 2 of the thirds, and the second fraction, that's going to be 1 of the fourths, right? And I want to be able to add these together. Basically, that means that I should end up with something that looks like this. My answer actually is just however much, what fraction of the whole is that? But it's not like you can just look at that and know, right? This is not one of those simple things where you can just look at that picture and be able to tell easily. So how can we get it? Well, one way to kind of approach this visually is, what if I was thinking about dividing these on these lines that I already have here? Notice I'm taking those dotted lines that already exist, I'm just kind of carrying those down. But while that kind of helps us divide it up into pieces, it doesn't tell us everything. I mean, it kind of can help, because notice the smallest pieces I get are these. I could kind of try to cut it up into those pieces. So if I did that, it'd be like having to divide those into pieces, like cutting them in half. And if I cut these in half, though, those pieces are too big. That's not the same size. So let's try cutting them up into 3 pieces there at the ends. And this actually could work for us. And so we can kind of see, yeah, this is where those cuts that we had to make in order to get the thirds and the fourths overlap. But the question is, how can we know where those are? Well, one way is we can go ahead and count those at this point. If we counted the number of squares that I now have in this rectangle, we'd find 12 squares there. And so, in order to get the final answer then, if I know that there are 12 squares that I can cut it up into, to get the final answer, I just count how many are shaded, well, 11 of them are shaded, over the total number of squares. So that's 11 of the 12ths, because each of those little boxes represents 1/12. So if I add them all up together, I get a total of 11 twelfths.
Why?
That's the visual way. Now, how do we know 12, right? Because that's really the big question. Where are these 12s coming from? Well, what we're looking for is we're looking to see how can I cut these up into equal size pieces. In other words, I can turn both 3 and 4 into the same number. And in this case, I can turn them both into 12. Now, why 12? Because 3 times 4 is 12. And so, in terms of the algebra work that's going on behind the scenes then, what I want you to do whenever you're doing the work for one of these is start by writing it like this. Very specifically, I mean, write it where you have the fraction plus or minus the fraction, but nothing on top yet. Because if you do that, that one little thing can make a big difference in terms of knowing how to go through this. Because this first fraction, the 2/3, I wanted to turn this 3 into a 12. What do I do to 3 to turn it into 12?
Multiply it by the 4.
We multiply it by 4. Yes. And so, if I'm going to multiply the bottom by 4, I also have to multiply the top by 4.
Oh,
where did you get 4?
Where did I get the 4? I got it because I'm saying 3 times what gives me this 12.
Oh, 3 times what gives you the 12, and then
Yep.
has to do the same on
now I
2?
see how you do.
And so then, that's how I know there's going to be an 8 up here. So let's take a look at the second fraction, repeat the same process. I say 4 times what gives me 12? Well, that's got to be 3. And so if I'm going to multiply that by 3, then I have to multiply this by 3. And so 1 times 3 gives me 3. And so I'm going to now go ahead and add those. And remember, the reason why I need the same denominator is because it stays the same when I add them. And so we get 11/12. Again, the basic idea here being that if I think back to that picture that we had up there, I took the 2/3 bar and I cut it up into pieces that were each a 1/12 big. So I could then see how many of them I had to add together. And for the 4th, I took that 1/4 bar and that shaded part of the 1/4 bar, and I cut it up into pieces that were each a 1/12 big. That way I'm adding the same thing together. Because whenever we add or subtract, we have to be adding the same things. Just like if I'm adding x's, they both have to be x's. One of them can't be an x squared or something. The same thing is true with fractions, where they have to be the same in order for us to add them together.
Oh boy, Mr.
Alright, so here's our next problem. And we're going to approach this one the same basic way. Our basic process is we start by seeing, what can I turn both the 5 and the 2 into? And remember, I got to do it by multiplying. So what can I turn both 5 and 2 into?
10.
Yeah, 10. I can make both of those into 10s. So on my paper, the first thing I do is I rewrite both fractions as over 10. But I haven't filled in the tops yet. So this is one of those things that by the time you just look back at the work, you can't tell just by looking at the work that we left that top empty at first. But it is one of those things where if you do it, it makes everything else make sense. Because you're now looking and just saying, 5 times what gives me 10? And what is that? 2, right?
2.
So since we have to multiply the bottom by 5, I also have, by 2, I have to also multiply the top by 2. That way it's still the same fraction. So 2 times 3 on top, that's going to give me the 6. Why do I multiply top and bottom by the same thing? Because if I reduce this fraction by dividing top and bottom by the same thing, I get back to the original. It's an equivalent fraction. That fraction equals the same thing as the original, just I cut it up into more pieces so that now I can compare it to the other one. So let's do it with the 1/2. Again, I'm trying to see what do I do to the 2 to turn it into 10.
5.
It's 5, yes. So I'm going to multiply by 5. And if I have to multiply the 2 by 5, I also have to multiply the top by 5. So that becomes a 5 there.
Is that 5 nice?
So, having gotten to that point, it now looks like the types of problems that you're good at.
Hello.
And so,
Tell me for my lyrics.
we go ahead and do the subtraction. We do the 6 minus 5 on top, which gives me 1. And the 10 stays a 10 on the bottom, remember. Alright, so in this problem, what usually ends up happening for our common denominator at this point is I see a lot of 48s. Because 6 times 8 is 48. So I know that I can turn both 6 and 8 into 48. Great. So, what do I multiply 6 by to get 48? 8.
Yes.
So that means I also have to multiply the top by 8. So that means I have 40 over 48 there. Then I go to the second fraction. 8 times what gives me 48? That's the 6. So then I multiply the top by 6 as well. So 3 times 6 on the top gives me 18.
Adios, mío.
And then we subtract, right? So 40 minus 18,
22.
that gives me 22 over 48. Remembering, of course, that the denominator stays the same. But what do you notice about this answer? Yep, we can reduce it. And so I now need to reduce this answer. And so to reduce it, that means I divide top and bottom by the same number. Notice I can divide both of them, in this case, by 2. So it gives me 11 over 24. Now the tricky thing about this one is that we are doing all of this work without our calculators. And for some of you, there might be 1 or 2 points in there where having a calculator would make a big difference to your accuracy. So this is perfectly fine if you did this work. But I'm going to show you another way where you could have done it as well. But I just want to be super clear. This other method, it's not the way that you have to do it, but it's another tool that you can have in your toolbox. The other way you could do it is get a common denominator of 24. Because, yes, I can turn both 6 and 8 into 48 by multiplying by each other, but they also both go into 24. And if you see that, you actually can make your life a little bit easier. Because then you say 6 times 4 is 24. So I multiply top and bottom of that one by 4. And the 8 times 3 gives me 24. So I multiply top and bottom of that one by 3. And once I see it that way, I go straight to the 11/24. There's no reducing necessary in that case. And the numbers I was working with were all a bit smaller. And so this makes it a little bit easier numbers to work with. So if you can see that this is an easier denominator to work with, you'll make the rest of your work a little bit shorter and a little bit easier to do. However, notice we started with the other one because I wanted to remind you, you don't have to. You don't have to get the 24. You can go to 48. It just means you'll reduce it at the end. So to practice all of your fraction skills, here's the same two fractions. Please add, subtract, multiply, and divide those two. All right, so for this first one, again, there's a couple different denominators you could choose to use. I first set up my two fractions with the addition between them. Now there is a lower denominator, and I'll show you what that one is here in a moment, but what if you just multiplied 6 and 3? You could turn them both into 18, and that is fine. And so that means I'd be multiplying the first fraction, top and bottom, by 3. And the second fraction, 3 times what is 18, is 6. And so I multiply top and bottom by 6. So that would give me 15/18 plus 6/18, which gives me 21/18. Can we reduce it? Yes. What can I divide both 21 and 18 by? 3. If I divide 21 by 3, I get 7. If I divide 18 by 3, I get 6. And yes, I'm okay with you just leaving your answer as 7/6 here. No need to go into mixed numbers. You can if you want to, but you don't need to. But I used a higher denominator than I actually had to here, which for some of you was tricky because for some reason you might have forgotten what you can divide 21 by or something like that, making reducing harder. So I could look at my 6 and my 3 there, and I could say, what can I turn them both into? Well, you notice 3 goes into 6 twice. And the 6, of course, is already a 6. I could have just gone and turned them both into something over 6 as well. This is shorter. It doesn't mean it's the way you have to do it, but if you see that you can use a smaller denominator like that, like 6 instead of 18, if you see it, do so, because as you can tell here, it made our job a lot easier. And I like easier. All right, so as you take a look at these, you can see the answers, but it's not just about the answers, it's about the process. Again, though, on this one, you could have used a different denominator here. You could have used 18. Some people use 12, that's fine. But it will still reduce to be the exact same thing. You'll still get 1/2 when you actually reduce it all the way down. The multiplication, straight across the top, 5 times 1 is 5. 6 times 3 is 18. That one doesn't reduce, so it's done. And then finally, for the division. Remember that for division, we flip the second fraction and multiply. I want to see that all in the same step. Sometimes I'll see people write first the 3/1 with division still in there, and then they'll go to the multiplication on the next step. Not only is it more writing than you have to do, but actually it's incorrect in that middle step. When we flip, it changes to multiplication. That has to happen all at the same time. And then once we do the flip, then it's multiplying straight across the top, straight across the bottom, and then reduce that fraction. In this case, I can divide top and bottom by 3.